What if machines could learn just like we do? Machine learning is about teaching computers to recognize patterns, not by programming every rule, but by showing examples. We feed the algorithm labeled data. Pictures of cats marked cat, emails marked spam, medical scans marked healthy or diseased. The algorithm searches this data, hunting for hidden relationships between the features we measure and the outcomes we want to predict. Each data point is a coordinate in feature space: height, weight, color, word frequency, pixel intensity. The machine doesn't see images or text the way we do. It sees numbers, measurements, patterns. The magic is in finding which patterns matter. This scattered cloud holds all the information we need. The algorithm's job is to make sense of it, learning patterns from labeled examples. This is supervised learning, learning from a teacher. The workflow has 4 stages. First, collect labeled data, thousands or millions of examples, where you already know the answer. Next, engineer features, transform raw data into meaningful measurements. Then, train the model, adjust internal parameters, until predictions match reality. Finally, test on new data you held back. Can it generalize to examples it's never seen? This pipeline turns raw data into intelligent predictions. Think of teaching a child by example. This is a cat, this is a dog. After enough examples, they learn to recognize new animals. The model does the same, learns a mapping, from input features to output labels. We split data into training and test sets to ensure it truly learned patterns, not just memorized. Generalization is the goal, working on data you've never seen before. Teacher plus examples equals trained model. How does the model improve? By following the gradient. Imagine you're standing on a foggy hillside, trying to reach the valley below. You can't see far, but you can feel the slope beneath your feet. Step downhill. Repeat. This is gradient descent. The model starts with random parameters, essentially guessing. It calculates how wrong it is, the loss. Then it computes the gradient. Which direction in parameter space reduces loss the fastest? Each step adjusts parameters slightly in that direction. The learning rate controls step size. Too large and you overshoot the valley, bouncing around forever. Too small and progress is painfully slow. With careful tuning, the model converges to a minimum, where loss is lowest and predictions are best. Finding the right learning rate is both art and science. Follow the gradient to minimize error. Supervised learning has 2 main tasks: classification and regression. Classification predicts categories. Is this email spam or not? Does this patient have the disease? What animal is in this photo? The model learns decision boundaries that separate classes in feature space. Regression predicts continuous values: house prices, temperature, stock performance. The model learns a curve or surface that best fits the data trend. Same learning engine, different outputs. Both use the same core engine. Training on labeled examples, optimizing with gradient descent. The difference is output type. Classification draws lines in the sand. Regression draws lines through the clouds. Medical diagnosis or house price prediction. It's the same fundamental learning process, adapted to the question you're asking. One model architecture, endless possibilities. Same learning engine, different outputs. Supervised learning powers the technologies we rely on daily. Medical diagnosis from X-rays. Fraud detection in banking. Voice assistants understanding speech. Self-driving cars recognizing pedestrians. Every prediction is built on patterns learned, from thousands or millions of past examples. The model is only as good as the data it learns from. Biased data leads to biased predictions. Incomplete data leads to blind spots. The patterns we find depend entirely on the examples we provide. Machine learning is a tool, powerful but not magic. It finds patterns but doesn't understand meaning. It makes predictions but can't always explain why in human terms, yet. As we deploy these systems at scale, fairness, transparency, and accountability become crucial. The algorithms we build today shape the world tomorrow. We must build them carefully, ethically, and wisely, learning from the past to shape the future.